Introduction. Today, Aarti and Rachna went to the market and then returned home. Aarti switched on the fan and the bulb. The fan was running at low speed, so Aarti rotated the regulator of the fan at its high speed. Rachna asked Aarti that how did the speed of the fan increase as you just rotated the regulator? How does it work? Aarti replied that the regulator of the fan works just like a variable resistor. At initial position, resistance was very high and the speed of the fan was low. But when I rotated the regulator, its resistance decreased to its minimum value and hence the speed of the fan maximized. It means that as the value of resistance decreases, the value of electric current increases. Students, today we will study more about the current electricity. Objectives. At the end of this lesson, you will be able to define electric current, understand electric current in conductors, define Ohm's law, calculate resistivity, know the limitations of Ohm's law, determine resistivity of various materials, evaluate temperature dependence of resistivity, define electrical energy and power, evaluate combination of resistors, understand cells and its combinations, state Kirchhoff's law, define Wheatstone bridge, meter bridge and potentiometer. Electric current. The electric current is defined as the time rate at which charge flows through a surface area. Let in time delta t, a net charge delta q flows through the area. The average electric current is given by delta q upon delta t. If the flow of charge is not steady, then the instantaneous electric current is given by dq upon dt. The SI unit of current is ampere. The current is in the direction opposite to the flow of electrons. The direction of electric current is taken to be in the direction of flow of positive charges. Electric current in conductors. For a current to flow in a conductor, a potential difference must exist across it. The current flows from high potential to low potential. When a battery is connected across the ends of a conductor, the surface charges of opposite sign build up on the conductor, starting from the two ends in contact with the battery terminals. These surface charges produce an electric field. This electric field causes electrons to move in a direction opposite to that of the field. Due to collisions, the electrons move slowly along the conductor and their average velocity is called the drift velocity Vd. This directed flow of electrons constitutes a current. Ohm's law. Ohm's law states that the potential difference applied across a conducting material is directly proportional to the current flowing through it. V is directly proportional to I, or V is equal to IR, where the proportionality constant R is called the resistance of the conducting material. The SI unit of resistance is ohm. Any electrical device offers a specified amount of resistance to the flow of current is called a resistor. We represent a resistor by this symbol. We consider a uniform electric field E exists along a wire of length L and cross-sectional area A. The potential difference across the ends of the wire is given by V is equal to EL, but I is equal to A upon rho L multiplied by V, where rho is equal to resistivity of the material. Put the value of I in the above equation. We get the value of resistance, which is equal to rho L upon A. We conclude that the resistance R of a wire is directly proportional to its length L and inversely proportional to its cross-sectional area A. Drift of electrons and origin of resistivity. When no electric field is applied, the random thermal velocities of the electrons produce no net current in any direction. When an electric field is applied, each electron experiences acceleration opposite to the field direction is given by A is equal to minus E, capital E, divided by M. Over a time interval delta t, the change in velocity of an electron due to the field E is equal to the product of acceleration and time interval. If tau is the average time between collisions, the average drift velocity of the electrons is equal to the product of acceleration and tau. The quantity tau is called the relaxation time. It is a measure of time for the system to relax back to thermal equilibrium through collision. Current density is given by J is equal to minus NeVd. Putting the value of Vd in the above equation, we get J is equal to Ne square tau upon M multiplied by E. Hence, conductivity of the material is given by sigma is equal to Ne square tau upon M, and resistivity of the material is given by rho is equal to M upon product of N, E square and tau. Mobility. The mobility of a mobile charge carrier in a conducting material is defined as the magnitude of the drift velocity per unit electric field. Mobility, mu, is equal to Vd upon E, which is equal to E tau upon M. Limitations of Ohm's law. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits where the proportionality of V and I does not hold. The deviations are of the following types. The relation between V and I depends on the sign of V. On reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction. V ceases to be proportional to I. There is more than one value of V for the same current I. A material exhibiting such behavior is gallium arsenide. Assessment. Before proceeding further, let us know how much you have learned. Click the correct option. Good job! Try again. Good job! Good job! Resistivity of various materials. Resistivity is an inherent property of a material. Conductors such as copper have small resistivity. Semiconductors are materials such as germanium with resistivity in a range of values intermediate to that of conductors and insulators. Insulators such as rubber have large resistivity. A color code scheme is used to indicate the resistance value of a resistor and its accuracy. A set of colored stripes are drawn around the resistor with their significance. Let's take an example. For the given resistor, yellow represents 4, violet represents 7, red represents 10 raised to the power 2, and gold represents 5%. On combining the above data, total resistance of the given resistor is 47 into 10 raised to the power 2 ohm with 5% tolerance. Temperature dependence of resistivity. The resistivity of a material depends on temperature. The relation between the temperature and resistivity is given by ρ is equal to ρ naught multiplied by 1 plus alpha T minus T naught, where ρ and ρ naught are the resistivity at temperatures T and T naught respectively. Alpha is called the temperature coefficient of resistivity. In metals, the resistivity increases with increasing temperature and alpha is positive. In alloys, the resistivity is very large but have weak temperature dependence. Alloy has residual resistivity even at absolute zero, while a pure metal has negligibly small resistivity at absolute zero. In semiconductors, the resistivity decreases with increasing temperature and alpha is negative. Electrical energy and power. Consider a portion of a circuit having current I and potential difference V between the two endpoints A and B. In a time interval delta t, an amount of charge delta Q is equal to I delta t moves from a point A to B of the circuit, and the work done by the electric field is equal to product of V and delta Q, which is equal to the product of V, I and delta T. The rate at which the electrical energy enters a portion of the circuit is called the electrical power input. P is equal to VI. The SI unit of power is the watt, W. Power dissipated in a resistor. When a potential difference V is maintained across a resistor, the free electrons in the resistor are accelerated by the electric field and gain kinetic energy. These electrons give up a part of their kinetic energy to the atoms in the resistor material when they collide with them. This transfer of energy to the resistor manifests itself as an increase in the temperature of the resistor. Power input to the resistor is given by P is equal to VI, which is equal to I square R, which is equal to V square divided by R. Combination of resistors. Two or more resistors may be connected to each other in certain combination to produce an equivalent resistance of any desired value. The equivalent resistance R of a combination of resistors is defined as the resistance of a single resistor, which can replace the combination without changing the voltage across the combination and the current I in the rest of the circuit. There are two ways of combination of resistors: series combination and parallel combination. resistors in series. Current through each resistor is the same current entering the combination. Potential drop across the series combination is equal to the sum of the potential drops across the individual resistors. For any number of resistance in series, R is equal to R1 plus R2 plus R3 plus and so on. The equivalent resistance is equal to the sum of the individual resistances. The equivalent resistance is always larger than the largest resistance in the series combination. Resistors in parallel. Potential drop across each resistor is the same. Total current entering the combination equals the sum of currents through the individual resistors. For any number of resistance in parallel, 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus and so on. The reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. The equivalent resistance is always less than the example. Let's take an example on combination of resistors. Calculate the resistance between A and B of the resistance network shown in the given figure. Let's see the solution. For calculating resistance RAB between A and B, we make an equivalent network shown in figure. Now we calculate resistance of arm GEFH, which is equal to 1 plus 1 plus 1 within parentheses is equal to 3 ohm. This is in parallel with the resistance of arm GH. So, the effective resistance between G and H is equal to 0.75 ohm. Now, RAB is equal to 1 plus 0.75 plus 1 is equal to 2.75 ohm. Hence, the effective resistance between A and B is 2.75 ohm. Assessment. Before proceeding further, let us know how much you have learnt. Click true or false. Good job! Good job! Try again. Good job! Cells. The cell can maintain a potential difference across a resistor to give a steady flow of current in the resistor. As the current keeps on flowing, the positive charges keep on accumulating at the negative terminal of the cell. Unless these positive charges on negative terminal are constantly transferred to the positive terminal through the electrolyte inside the cell, the potential difference across the two terminals cannot be maintained constant. Work is required to be done for transferring the charges from one terminal to the other through electrolyte inside the cell, since the electrolyte medium offers resistance against the movement of charges. This is called the internal resistance of the cell. EMF. The work done per unit charge to force charge to move from lower to higher potential terminal inside the cell is called the electromotive force of the cell. EMF of the cell is given by E is equal to I within parenthesis capital R plus small r. Here capital R is the external resistance, small r is the internal resistance, small I is the current in circuit. An ideal cell has a zero internal resistance. The voltage applied to the circuit is equal to the EMF of the cell. Cells in series and parallel. Cells in series combination. In series, cells are joined end to end so that the same current flows through each cell. In ordinary series connection, the positive terminal of one cell is connected to the negative terminal of the second, the positive terminal of the second to the negative terminal of the third, and so on. When cells are connected in series, the EMF of the battery is equal to the sum of the EMFs of the individual cells. The total internal resistance is equal to the sum of the individual internal resistances of the cells. The current in each cell is the same and is equal to the current in the entire series combination. If n identical cells, each of EMF E and internal resistance R, are joined in series, the current in the circuit is equal to NE divided by R plus NR. Cells in parallel combination. Cells are said to be connected in parallel when the current is divided among the various cells. In ordinary parallel connection, all the positive terminals of the cells are connected together and all the negative terminals are connected together. When identical cells are connected in parallel, the EMF of the battery is equal to the EMF of a single cell. The reciprocal of the total internal resistance is equal to the sum of the reciprocals of the individual internal resistances of the cells. The current in the external circuit is divided equally among the cells. If n identical cells, each of EMF E and internal resistance R, are joined in parallel, the current in the circuit is equal to NE divided by NR plus R. Kirchhoff's laws. First law states that at any circuit junction, the sum of the currents entering the junction must equal the sum of currents leaving the junction. The algebraic sum of the currents entering or leaving a junction is 0. Summation of I is equal to 0. Second law states the sum of the potential changes across all the circuit elements found when traversing in one direction around any closed circuit loop must be 0. Summation of delta V is equal to 0. Wheatstone bridge. The Wheatstone bridge is a device that can be used for measuring an unknown resistance. It consists of a battery, a galvanometer, and a network of 4 resistors. Current I flows from the battery into junction A, where it divides into current I1 and I2. The galvanometer segment between junctions C and D forms the bridge. By adjusting the values of the resistances, the current in the galvanometer is made zero, as indicated by zero deflection. At this condition, the bridge is said to be balanced. The condition of the balanced bridge is R1 upon R2 is equal to R3 upon R4. A Wheatstone bridge is most sensitive when the resistances R1 and R2 are of the same order of magnitude. Meter bridge. A meter bridge is an application of Wheatstone bridge. The apparatus is essentially a slide wire bridge in which a uniform resistance wire of length exactly 1 meter is mounted on a wooden board between two fixed terminals A and C, along with a parallel meter scale which can measure any partial length of the wire. Across the whole wire length AC, we connect the cell. One end of the galvanometer is connected to the middle copper strip at point D, and its other end is connected to a jockey which can be connected to any required point on the wire. A resistance box is connected across the gap G1 and unknown resistance is connected across the gap G2. At the balanced state, we have S is equal to product of R and within parenthesis 100 minus L upon L. To calculate the value of unknown resistance, we have to calculate only the balancing length accurately. Potentiometer. Potentiometer. Potentiometer is generally employed to compare the EMFs of two cells or any two sources of EMF. Potentiometer may also be used to determine the internal resistance of a cell, to measure current, to calibrate an ammeter or voltmeter, to compare resistances, and for the measurement of thermoelectric EMF. Principle of potentiometer. Potentiometer works on the principle that the potential difference across any length of a wire of uniform cross-section and uniform composition is proportional to its length when a constant current flows through it. The smaller the potential difference that can be measured with a potentiometer, the more is the sensitivity of the potentiometer. The terminal A of the potentiometer is connected to its terminal B through a battery, an ammeter, a rheostat, and a one-way key. The positive terminal of the given cell, whose internal resistance is to be measured, is connected to the terminal A of the potentiometer, and the negative terminal is connected to a slider S through a galvanometer G and a resistance box. The internal resistance of the cell is given by R is equal to L1 minus L2 upon L2 multiplied by R. Here, L1 is the balancing length when K2 is open. L2 is the balancing length when K1 is open. Assessment. Before proceeding further, let us know how much you have learned. Drag and drop the correct option. Did you know? George Simonome wanted to measure the motive force of electrical currents. He found that some conductors worked better than others and quantified the differences. He waited quite some time to announce Ohm's law because his theory was not accepted by his peers. The unit for resistance is named after him. Lightning is a discharge of electricity in the atmosphere. Lightning bolts can travel at around 210,000 kilometers per hour while reaching nearly 30,000 degrees Celsius in temperature. A resistor placed in a series with another component, such as that of a light-emitting diode, reduced the current to a known safer value. A battery explosion is caused by the misuse or malfunction of a battery, such as attempting to recharge a non-rechargeable battery or short-circuiting a battery. Car batteries are most likely to explode when short circuit generates very large currents. Summary. Let us summarize what we have learned. The electric current is defined as the time rate at which charge flows through a surface area. Due to collisions, the electrons move slowly along the conductor and their average velocity is called the drift velocity. Ohm's law states that the potential difference applied across a conducting material is directly proportional to the current flowing through it. The mobility of a mobile charge carrier in a conducting material is defined as the magnitude of the drift velocity per unit electric field. The equivalent resistance of a combination of resistors is defined as the resistance of a single resistor, which can replace the combination without changing the voltage across the combination and the current in the circuit. The work done per unit charge to force charge to move from lower to higher potential terminal inside the cell is called the electromotive force of the cell. Kirchhoff's first law states that at any circuit junction, the sum of the currents entering the junction must equal the sum of currents leaving the junction. Kirchhoff's second law states that the sum of the potential changes across all the circuit elements found when traversing in one direction around any closed circuit loop must be zero.